Hello, everyone. Welcome to the 11th live session of Bigan Chacha Asor. Bigan Chacha Asor works to promote scientific temperament among students. We also fight against all kind of superstition. Today, we are blessed to have Professor Amitava Datta with us. Amitava Datta is a professor of computer science at University of Western Australia. One of his research interests is in quantum algorithms and quantum information processing. He loves to teach and supervise students in computer science, molecular biology, and physics. I request Professor Datta to start his presentation.
Thank you, Sobasachi, and thanks a lot to Bigyan Charasur for giving me this wonderful opportunity to talk to so many students and other friends and other people. And today, so I chose a slightly non-standard topic which may not be very familiar to everyone, but we'll see that it is very interesting. So it's about quantum non-locality, and I have prepared it in a way that it should be accessible to everyone. So, since we have a very broad audience, I will just give a very brief introduction to quantum mechanics, a brief note. Quantum mechanics is behind almost all progresses that you see around you and in the last 100 years. Almost all the comforts of life that we enjoy are due to quantum mechanics. For example, all of you are watching this on your phone or tablet or laptop. All those are due to quantum mechanics. Colloquially, we say that electronics has revolutionized our civilization, but actually, what is behind electronics is quantum mechanics. We have understood semiconductor devices, that is the backbone of electronics, due to quantum mechanics. So that's about technology, but fundamental science, almost everything that we know or we have understood in the last so many years, 100 years. For example, physical phenomena like how stars work, or even how the different parts of our cells in our body work. Those are all due to quantum mechanics. So this is, we should keep in mind that this is the most wonderful theory that has been invented by humanity, and it has delivered tremendous progress in the last 100 years. So, quantum mechanics was proposed in 1925, exactly 100 years ago. This is not a talk about quantum mechanics, so I can't go into the history of it. Perhaps I'll get an opportunity in future again to talk about that. But today's talk is about one aspect of quantum mechanics. I call it a mystery because I don't understand it. But whatever little I understand, I'll try to explain to you. It is quantum non-locality. So I'll try to explain this using very simple logic that we are familiar with. There is no mathematics in this talk, and a few things, perhaps you have to take my words when I am giving the presentation, but you can always ask questions that I will try my best to answer during the question and answer session. So, if we have to understand quantum non-locality, we have to understand quantum superposition. So let's look at some classical randomness first. Now, if you haven't seen this coin, then you are very young. We used to buy lozenges and other goodies in our childhood with this coin. I had to take a coin that has been out of circulation for some time due to copyrights. So what is our experience when we see a coin like this? We can keep a coin on a table or in a box, and it will show either head or tail. I am assuming that it can't stand on its sides. So that is our everyday experience. If we toss a coin, everyone knows how to toss a coin. We get head sometime and tail some other time, and we often call it the randomness or random coin toss. Now, the fact is, this randomness is due to our lack of knowledge. If we know the exact force when we are tossing the coin, how the coin is made, whether it is a balanced coin or one side is heavy, etc. If we know the air temperature in the room, humidity, if we know everything, we can exactly say whether it will fall head or tail. So these are the hidden information for our coin toss. A coin toss will not look random if we use all this hidden information. Now, the situation is quite different in quantum mechanics. In quantum randomness, a quantum coin is both head and tail at the same time. It does not have a definite state if we do not look at it. Now, in this talk, I'll try to avoid physics as much as possible. So I'll not clarify the meaning of looking at it. But again, there is the Q&A if you are curious about it. So if we look at a quantum coin, it will sometimes show head and sometimes it will show tail. But we don't know beforehand what it will be. This sounds very strange. Actually, it takes a very long time to get used to this phenomenon. And you may think that it seems so since we are missing some hidden information, just like tossing a coin in the previous slide. But the fact is, it is much deeper than that. It is not possible to understand or know any hidden information that can tell us whether the coin is, I use the letters H or H for head and T for tail. So no hidden information can tell us whether the coin is H or T if we do not look at it. In fact, we cannot talk about its, in quantum language, we call it state. There are two states for this coin, H or T. We cannot talk about any of these states. This is called quantum superposition. I have made the coin hazy because you can imagine that it is spinning very fast, and so that it is neither head nor tail facing you. So an object stays in two possible states at the same time. And in quantum mechanics, we write that as H plus T. That means it is head and tail at the same time. This is called superposition. and we have to digest this in order to go into quantum non-locality. So you can see I have used up my first mathematical symbol, which is a plus sign. So to re-emphasize, suppose I have a box. I put a classical coin, the coin of our daily experience. We keep it in the box. We know, suppose when we keep it in the box, we know it is T or tail. It will remain tail when the box is closed. I can say for sure that the coin is in the state tail. And when we open the box, we'll find it tail. So there is no problem there. In quantum we keep it in the box. We cannot say whether it is H or T. And when we open the box and look at it, find in the state. So quantum probability or quantum chance is very different from classical probability. Classical probability arises due to lack of information. Quantum probability is an implicit property of nature as far as we understand. So, everyone knows this gentleman, Albert Einstein. He wrote a letter to a Hungarian mathematician, Cornelius Lanczos, in 1939, I think. So he wrote, "It seems hard to sneak a look at God's cards, but that he plays dice and uses telepathic methods is something that I cannot believe for a single moment." So what Einstein means by playing dice is that the quantum chance or quantum probability that we cannot delve deep into the world of nature to understand this probability. So today's talk will talk about the telepathic methods that he mentions in the second part of this sentence. In fact, if you look at Einstein's quotes, quite often people leave that second part out. But the second part is more interesting, more troubling. And I have a suspicion, reading history and reading the history of quantum mechanics, that Einstein was more troubled by the telepathic methods. So we'll mainly talk about the telepathic methods, but we have to use the playing dice part to understand this. So let's look at two quantum coins. Two will be enough for us. So we have seen that one quantum coin, if we look at it, we find either H or T. So what do we find if we look at two quantum coins? We may find HH, both heads, H and heads and tails, head and tail, tail and head, or tail tail. So these are the four possibilities. If I have millions of quantum coins and if I look at them, millions of quantum coins, then I find almost all these combinations. So is superposition of all these codes. Algebra, and what we can do is look at these first two terms and we can take the h out and we get h plus t. From the second two terms you can take the t out, we get h plus t.
একটু
think
টেকনিক্যাল অসুবিধা হচ্ছে। আপনি জাস্ট পিপিটিটা একটু লগ ইন করে দিন।
কি করব?
পিপিটিটা আরেকবার লোড করে দিন। আপনি
আচ্ছা,
ইন্টারনেটে এর জন্য বেরিয়ে গেছেন। সবাইকে অনুরোধ প্লিজ ওয়েট ফর a moment. There's a little bit technical glitch. Uh, I, I, I'm sure that it will be solved within few minutes.
PPT is uploaded and yeah.
Yeah, it's ready.
Okay, sorry everyone for this glitch. So what I was trying to say is, if you consider this superposition, then we can write the first coin as h plus t and the second coin as h plus t. In other words, they are not, they are separated. They live in separate world. Actually, there is a technical term for this in quantum mechanics, but we'll avoid physics. So this is a good situation. Good in the sense that the first coin is independent of the second, and the second is independent of the first. So, but the mathematics of quantum mechanics tells us that we called it a state, that a state like HH plus TT is possible. In fact, it is routinely created in laboratories all around the world. And this is a problematic state because, unlike in the previous case, we cannot factor out the two coins in separate worlds. This is possible. This is also possible. HT plus TH, and these are called entangled states. They are a superposition of both H, both T, HT, TH. So, in a sense, both the coins live in a common world. They are somehow connected to each other. And that is why, if this gentleman is one of the legendary physicists, Erwin Schrödinger, he gave the name entanglement. Not only that, he emphasized that this is the most defining feature of quantum mechanics and how quantum mechanics is different from our classical experience. Why it is defining, I'll not go into it, but you can ask me later if you are curious. So now let us go back to a bit of history. In 1935, Einstein, Boris Podolsky, and Nathan Rosen, who was Einstein's secretary, they pointed out a very troubling feature of quantum mechanics. Now, in all these discussions of quantum mechanics or quantum information, there are two characters. One is Alice and another is Bob. Sometimes Charlie also appears, depending on what we are trying to understand. So suppose Alice and Bob prepare the state HH plus TT. Alice keeps the first quantum coin. This is a joint state of two quantum coins. Alice keeps the first quantum coin in her home on Earth, and Bob takes the other quantum coin to the end of the universe. You can imagine however far you can imagine. Now, the problem is this. If Alice looks at her quantum coin and finds it as H, Bob will instantaneously find his quantum coin to be H. Because you see, if Alice finds H, that means we call it branches of state. So Alice basically excludes this branch if she finds her coin to be H. And Bob's coin becomes instantaneously H. Or the other case, if Alice finds her coin to be T, Bob finds his coin to be T instantaneously. Now, this is very problematic because Einstein thought, or Einstein emphasized, that quantum mechanics must be incomplete, because how can Alice, whenever Alice measures or looks at her coin, how can that information be communicated to Bob's coin at the other end of the universe? Now, you may wonder that we really can't go to the other end of the universe. So, why I am saying this? If you want to know, I can explain further. We can create the other end of the universe in the lab. So, we'll go to that in the question answer session. So let us look at some philosophy. I know many of my friends, they don't like philosophy. Physicists don't like philosophy, but I'll not discuss much of philosophy. But if we discuss quantum non-locality, we have to discuss a little bit of philosophy. So Einstein was a firm believer in realism. What is realism? Realism is the fact that if every object that we encounter in our daily lives, they have definite properties. The table is there, even if I don't look at the table. It's not that by looking at the table, I bring it into existence. So objects have definite properties whether we look at it or not, but we just saw that a single quantum coin is neither head nor tail until you look at it. And we have now a lot of evidence that realism is dependent on observer in the microscopic world, at least, when things are very, very small. But the fact is, this is very, very troubling, and it troubles a lot of very serious people. These two gentlemen here, they are two of the most influential physicists in the second half of the 20th century. Gerard Dupont and Roger Penrose, they don't like a bit of it. For example, Dupont in a recent interview raised the question, is the moon there if we don't look at it? And Roger Penrose is more forthright. He straight away says quantum mechanics must be wrong. So that is realism. And what is locality? Now, locality was a bedrock of classical physics before quantum mechanics. Locality is very simple to understand, and we have daily experience of locality. If I push a table, the table moves. If I push a table here, the table in your house doesn't move. So if I do something here, the effect will be local. For example, Einstein's theory of general relativity is a local theory. If the sun disappears suddenly, we won't feel it for 9 minutes, because that information will take 9 minutes, or I don't remember exactly, something like that, to reach us. And in particular, due to a very famous theory that Einstein proposed in 1905, any effect in this universe cannot propagate faster than the speed of light. Now, the joint state of two quantum coins, HH plus TT, it has been experimented thoroughly, and very recent experiments, I can tell you, I think in 2021, that when Alice looks at her coin, Bob's coin becomes either H or T, depending on what Alice sees, at least 100,000 times the speed of light. So this is non-locality. what is happening is some effect is propagating faster than the speed of light. Einstein disliked it perhaps more than the probability inherent in quantum mechanics. So Einstein's idea was, is quantum mechanics incomplete? He thought it was incomplete. There are hidden variables, just like our classical coin, where there are hidden information about the material, how the coin is made, how much force we are tossing it with, and etc. So Einstein thought that sort of hidden information we can add to the description of quantum mechanics, so that this he called this Alice and Bob story as spooky action at a distance. So he thought it will go away. So what was the idea behind that? The hidden variable or hidden information, that for HH plus TT, the two coins have decided secretly what Alice will see for the first coin, and then what Bob's coin will do. So Einstein thought there is some kind of secret agreement between the two coins, even though they are at the two ends of the universe. That would have solved the spooky action at a distance problem, and also the problem of realism, perhaps. And to tell you the truth, I haven't found any concrete evidence, but people suspect that Einstein worked on this long and hard to propose an alternative theory to quantum mechanics, but he died in 1955. Now, mainstream physicists did not bother about all these problems. It was a vague and unnecessary philosophical question. Why bother when quantum mechanics was giving so many outstanding results? For example, as I explained in the very beginning, that semiconductors we understood and we built whatnot, televisions and wireless equipment and mobile phones and so on. So why bother about all these philosophical questions? Now enters this gentleman. He was an Irish physicist, John Stuart Bell. He worked at CERN in Geneva as a particle physicist, and as his hobby in his free time, he used to think about all these philosophical questions. And remarkably, he converted this philosophical question into a physics experiment in 1965. Not many people noticed it, but it has gradually been recognized by mainstream physics. And the way he converted this into a physics experiment is really the second part of our talk. Now, look at the problem. Alice and Bob, they have two quantum coins in this state, HH plus TT, and this problem is actually about correlations. What Alice sees is correlated with what Bob sees. For example, if Alice sees H, Bob will see H. So there is a connection or correlation between what Alice and Bob see. If they have many pairs of these coins with this state HH plus TT, and Alice measures her coin, and later on they come together. Bob travels from the other end of the universe, and they tally their results, and they see this remarkable thing that whenever Alice measured head, Bob also saw head. So this, how to convert this into physics experiment is really the contribution of this gentleman, John Bell. And some people say that this is one of the most profound theorems in whole of science. It is not a theorem of quantum mechanics. Bell's theorem is not a theorem of quantum mechanics. It simply says, give me two theories. I'll tell you which one gives higher correlations in this sense. Along the way, Bell's theorem says something very profound about the two sort of philosophical issues that I mentioned just now, realism and locality. It says that you cannot have both at the same time. If you want realism, you have to abandon locality and vice versa. So let's see. In the second part, I'll try to explain what John Bell did. And what John Bell did has been simplified by four people pretty soon after Bell proposed his theorem. Clauser, Horn, Simony, and Holt in 1971. And that simplified version was experimentally verified first by this gentleman, John Clauser. Then the most famous experiment was done by Alan Aspe, and Anton Zwillinger also contributed to this experiment. They received the Physics Nobel in 2022, if you keep track of it, by verifying the CHSH inequality experimentally. Now the problem is, it is not mathematically very difficult to understand the CHSH inequality. However, you need to know a little bit of the mathematics of quantum mechanics to go into the exact details. So I'll not try to do that. I'll just try to explain a still simpler version of the CHSH inequality called the CHSH game. So the CHSH game is not technically complete, and but it captures the flavor of Bell's theorem or CHSH inequality quite correctly. And it is a very fun game. So I'll try to explain to you that game. Now, this is the setting of the CHSH game. There are two players, Alice and Bob, of course. They always play quantum games. They know they will be asked four questions by a referee, Charlie, let us say, and they will win the game if their answers for each question are correct. So Charlie has these four questions, and he will randomly ask the same one part of the question to Alice and the other part of the question to Bob, and their answers should match in for three questions. So this is the critical point, that their answers must match for three questions. What does that mean? For example, if Alice's answer for one of these three questions is yes, and Bob's answer is also yes, they win that question. So they score a point. They also win if both answers are no. So both should match. But there is a fourth question where their answers must be just the opposite. If Alice says yes, Bob must say no, or vice versa. So this is the game. Now, Alice and Bob know the rules of this game, but they don't know which question requires the opposite result. They know three of them requires the same result, same answer from them, but the fourth one requires just the opposite answer. Now we can simplify the questions as 0 and 1 because we don't want to go into details of the questions. There is a referee who randomly chooses the four questions 0, 0, 0, 1, 1, 0, or 1, 1. There is no particular meaning about these numbers. So to explain to you again the rule of the game, the referee can ask four equally likely questions. Three questions demand give the same answer. One question demands give different answers. Alice and Bob know the rules of the game, but do not know which of the four questions requires a different answer. Now, during the game, they are not allowed to communicate. They are put in two different rooms with closed doors and sealed everything, and they cannot communicate. But before the game starts, they can discuss as much as they want or wish, and then they go into these two separate rooms. So, what is the classical strategy that Alice and Bob should adopt? It's a fun game. You can play yourself, um, even though your name is not Alice or Bob, but you can catch a friend and play this game. The first option is always give the same answer. Doesn't matter what is the question. Always say yes. Both Alice will say yes and Bob will say yes. So in that case, they will win all the first three questions, not first three, I shouldn't use the word first, but three questions that demand the same answer, but they will lose the one which demands different answer. So they win three out of four. Not bad. That is about 75% success. Option B is try to give different answers sometime. Now they might win the different question in this case. If they're lucky, they will win all four. But statistically, if the referee, these games are played statistically. That means the referee asks the four questions again and again and again. So statistically, they cannot win more than three out of four. Because if they choose different answers sometime, they will lose one of the questions that expects the same answer. So look at this. I mean, even though we are playing this simple game, but what we are talking about here is realism. That means Alice and Bob have decided their strategy, they have written down their answers on paper or maybe on their mobile phone, and they have gone to the separate rooms. So that means the questions have real values, or the answers of the questions have real values before the game starts. So this is realism. Just like our classical coin had real values, head or tail, before we toss, and we know everything about the hidden information. So they have always real values. They have real values to start with, in midair, when they land. So this is realism. So you can say that, okay, why don't they choose answers by flipping a coin? Actually, it can be shown easily that flipping coins is just uh, taking strategy A sometime. That means answer all every time the same answer, or sometimes strategy B. In On an average, you cannot do better than 75%. So classical players, here Alice and Bob are playing according to classical, what our everyday experience. Classical players must choose in advance which rule to violate, and that costs them at least one out of the four questions. So classically, you cannot do better than 75% by playing this game. Let's look at quantum. Now, as we have seen, In quantum mechanics, Alice and Bob do not pre-decide their answers. We haven't seen it, but we will see soon that Alice and Bob do not decide beforehand their answers. They ask their coins for the answers. Now, this is very weird because in classical situations, every one of us know that if a coin is lying on the table, how can you ask the coin anything at all? It is head or it is tail. But we can ask the coin questions when we drop realism because the coin doesn't have any fixed value. We can ask the coin very cleverly so that we get some value, sometime head and sometime tail. So the answers do not have any existing values, like the previous case when Alice and Bob wrote down their, they discussed a lot and wrote down what they will answer in their mobile phone, notepad, or someplace. So step one is take entangled quantum coins. Entangled means like HH plus TT. Alice and Bob share one each. Alice takes one of the entangled coins and Bob takes another entangled coin. And before the game starts, no coin has a definite head or tail according to the rules of quantum coin that we have seen. Now, step two is questions choose how to look. So when Alice and Bob get the question will tell Alice and Bob how to look at one of their coins, not what answer to give. They don't know, they haven't written down the answer, but which question to ask the coin. And different questions that Charlie asks will tell them to look at the coin differently. Now, again, I am avoiding physics, but if you want to know what looking at means, we'll come to that. But still, I have a picture here. So, looking at quantum coins do not have a definite property. I have told you now 100 times. A coin may be head or tail when you look at it. This allows us to look at a quantum coin at different angles. We can increase the probability of finding the coin as H if the angle is closer to H, and vice versa, similarly for T. So those of you who know a little bit about vectors in your physics school curriculum, then you know that if some vector is close to some other line, then its component will be larger on this line compared to the component of this tail. So by changing the angle of looking, we can extract probabilistically head or tail more often than not. So that is the strategy. Now, we have to, I hope you'll go home and won't sleep and lose your sleep over this. So quantum strategy, what it is saying, Alice and Bob do not store their answers beforehand, like in the classical strategy. They look at their coins at different angles depending on the questions, and that is the great freedom of quantum logic. It gives the freedom of extracting an answer with different probabilities if we wish by changing the angle of looking at it. The answer is not fixed. Now, this is the CHSH game. It avoids the technical part of it, but this game can be easily converted into the so-called CHSH inequality, and we have seen the maximum success Alice and Bob can get by using the classical strategy is 75%, and basically John Bell proposed using the mathematics of quantum mechanics that the success can be increased, the correlation between what Alice and Bob see can be increased to 85% with the quantum strategy. And Clauser, Aspe, and Zwellinger verified that, because just saying it using the theory is not good enough. You have to show it experimentally. Now, what did we learn then? We learned that nature is not classical deep down. Our everyday experience breaks down when we look at microscopic things or small things. Actually, that is a big problem in quantum mechanics. Quantum mechanics doesn't tell us when things become like our everyday experience and when they remain weird like this, like our quantum coins. That is a huge area of research. I hope I'll understand someday. So, nature is quantum. There are definite answers to questions in the classical world because objects have definite properties. Objects do not have definite properties in the quantum world. Properties emerge when we look at the objects. So basically, Bell's theorem that I told you, that along the way it solved some philosophical problems. It says, I cannot go into too much details, even though I love philosophy. Local realism is dead. If we insist on realism, that objects have definite properties, even if we don't look at them, we must accept spooky action at a distance. We must accept that they are talking to each other in some way across the diameter of the universe. If we don't like spooky action at a distance, we must accept that there is no realism. Objects don't have any definite values until and unless we look at them. Are there hidden variables that can always predict whether a quantum coin is H or T when you look at it? Just like the classical coin, we saw that there are hidden information, pieces of hidden information. Actually, Bell's theorem rules out local hidden variables. That means hidden information that is purely local to Alice and purely local to Bob. But that is a fascinating and complicated story. Actually, this is my last slide. Now, it was not a talk on quantum mechanics, so I haven't shown you pictures of many important proponents of quantum mechanics, but I can't give a talk on foundations of quantum mechanics without showing the picture of this gentleman, John von Neumann, the quintessential genius of 20th century. Actually, if you keep track of science news, you'll see that every day there is news about quantum computing, quantum information, quantum key distribution, and all sorts of things. It has been made possible partly by John von Neumann because he made quantum mechanics into an axiomatic theory, basically just like any mathematical theory. But John von Neumann in 1933 proved a theorem that no hidden variable theory can replace quantum mechanics. And some people argue that it may be the only wrong theorem he had proved in his life. May not be. I cannot go into the details of this dilemma. You can ask me. I know a little bit about it. But at least it is true that no local hidden variable theory can replace quantum mechanics. Actually, this gentleman, David Bohm, in 1953, gave a non-local hidden variable theory. That means the hidden variables are not entirely with Alice nor with Bob. They are connected in some sense. The so-called the Broglie-Bohm bilateral theory, we cannot discuss that, but quantum coins in their theory or Bohm's theory always have definite values, but it is ultimately non-local. If something happens to a particle here, it affects all the particles in the universe. David Bohm showed his theory to Einstein. Einstein didn't like it at all due to this extreme non-locality. So, thank you very much for your time. I may answer all your questions, or following quantum mechanics, I may not. Let's see.
Yeah, thank you very much, Amitava Datta. Uh, the talk was really marvelous. It is even special because you completed that talk without using any of the equation. So I guess you remember the the Stephen Hawking's quotation that if you introduce one equation, you may lose half of your audience. So so
Yes.
so you didn't take any chance for that, and and you have not used any of the equation, and it was a really nice, and I'm pretty sure that the students will learn a lot about the topic, though the topic is not as simple as Amitabh described. Amitabh tried his best to make it simple, to give a feeling that it looks simple, and I guess that the students will be encouraged to take study further, so that they can learn a lot, because we know that the quantum computation is coming. Already knocking the door, and our government is taking preparation for that. Our institutions are taking preparation for that, and everyone of us have to be aware of that. We need to learn it quickly if you have not already started. So, Amitabh, you mentioned about that one can create the one can go to end of the universe, maybe
Yes.
by thought experiment. So can
Yeah.
you elaborate a bit more about that?
Yeah. Thanks. Thanks for asking. Actually, what really is improving is how fast you can measure. Now we have atomic clocks which can measure time in attosecond level, 10 power minus 18 second. And in 10 power minus 18 second, light travels zero point 0.3 nanometers. So if you can have a laboratory setup which is even 1 meter apart, and you can what Alice does, and within an attosecond you can check whether Bob's state has collapsed to the corresponding state, then it is effectively like end of the universe, because or maybe Andromeda, let us say.
Yeah, yeah, almost, yeah, yeah.
But our
It's
measurements are improving, so we can make it further and further. So that's the logic behind end of the universe.
Yeah, and nowadays everyone is talking about quantum computations. It's going to be the next reality. But still, the use of quantum computation, it's only very few people, or maybe say very few institutes can use it, like Google's. So, can you predict that how long it will take, so that everyone, the common people, can the technology will be uh, so simple or so cheap, so that most of the people can afford it?
Yes. The first point is that most of the people may not need to use a quantum computer,
Yeah, yeah, that's true.
because quantum computers are very special devices, and also quantum computing itself has a very interesting history. It was proposed in the 1970s by Richard Feynman, and Feynman's idea was that if you want to understand quantum simulations, because even now we simulate quantum systems by classical computers, but classical computers are not the ideal instrument for simulating quantum systems. So his idea was we'll simulate quantum systems by quantum computers, which makes sense because at the heart of quantum computation is massive superposition. I just showed you superposition of one coin, but actually they are called qubits. And massive superposition is required for simulations in quantum chemistry, in material science, and etc. So most probably the main use of quantum computers will be in simulating quantum systems. If you ask me general purpose computing, we don't know yet. I mean, this the hype is so much that we still don't know. People don't know that we don't know what problems are suitable for quantum computers. So
Yeah,
that is a very fundamental problem. So I am not really along the hype in that sense, but on the other hand, no one can deny that simulating quantum systems, quantum computers are the best uh,
yeah,
instruments.
yeah. And I guess that the day is not far. If not, everyone can use the quantum computation, but it will be more affordable. Maybe within a decade or so. Yeah,
Yeah,
the tech.
actually, main problem with quantum computation or quantum computers is to maintain these quantum superpositions. They break down very fast. I mean, what I can go a little bit into this. The word I used looking at a quantum system, it is the measurement problem. Or measurement of a quantum system. So, very large superpositions tend to get measured automatically by interacting with the environment. So, this is called quantum decoherence.
Yeah,
So, that is why to maintain them, for example, current technological landmarks are maintaining quantum superpositions for milliseconds.
okay.
So if you have to do a quantum computation, you have to do within milliseconds. So you can
Okay.
see that how large a computation you can do is restricted by how long you can maintain this kind of superposition. It is improving. There are different technologies that are being proposed. So hopefully it will improve and we'll be able to maintain quantum superposition. And the second problem is quantum error. So basically, these qubits, let us say head and tail, head becomes tail, tail becomes head. This is called bit flip. And also, I wrote always H plus T. Actually, that plus sign is tremendously significant. I think Feynman wrote in his third volume that all the mysteries of a quantum bit is in the relative phase. So H plus T and H minus T are very different things. So due to error, that sign flips. So if you have to do a serious computation, you have to correct these errors from time to time. And that is
Yeah,
another problem that is limiting the current technology.
yeah. So plenty of challenges are there, but I guess that
Yeah.
you are still, yeah, you are still working on that, and there's bright future,
Definitely.
yeah, for the quantum competition, and especially students, as I can learn that our government is taking special measures to improve the education in quantum computations. Different IITs and other institutes are already preparing for making us uh, different branches on quantum computations, so to develop expertise and other things. So students, if you are interested, you can learn more. So you can take today's session as a introduction to the subject, and we are lucky that Professor Datta described through the complicated subject really nicely and simply, so that I guess that students will be benefited from this session. And I thank Professor Datta again for this beautiful session, and I thank everyone to be with us. So we are going to stop to the good night.
Good night.